We're going to talk about Ancova today. So it's an ANOVA with a C in the middle, analysis of covariance. And first I'm going to talk about using different ways to answer the same question. And this will be one of the problem questions on your exam, final exam. So I will give you a scenario and then ask you to analyze it with different ways. And then if you were to do it this way, what would be the IVs, what would be the DVs, what would be the covariates. So I think the main purpose is to help you look at a question and then think of, okay, what kind of analysis to pick, and then know that you can use different types of analysis to address a similar question. Results might not be the same, and so sometimes if it doesn't work out with one, you can try another one. That's sometimes what we do in the real world. So this is an experimental design where we have pre-test and post-test and have a treatment group and a control group. So in an eyeballing, what kind of analysis will we do for this kind of treatment? If I wanted to, this kind of design, if I wanted to know whether treatment group was better than the control group in lowering anxiety scores. So these are anxiety scores pre-treatment, post-treatment. I wanted to know if treatment group had lower anxiety scores. Was treatment effective? What are some ways to analyze this? We randomly assign participants to be either in the treatment group or the control group. Factorial analysis. Say more about that.
They're totally different participants, right? In both groups.
So there's between groups.
Yeah. And then there's two different groups.
Two,
right?
this
Treatment
group
and not in control.
Yes.
Yeah.
So that would be one IV would be treatment and control.
Oh, but is this at two different times?
Yes, this is two different times.
So repeated.
So mixed.
Mixed design.
Oh, because it's with one between group. Yeah. Okay.
Yeah. So so one way, yes, exactly. So one way is to look at it in terms of using a mixed design. Like, okay, there are two different groups. One is receiving treatment and one is control group. And are there changes in the anxiety scores, same or different across these two groups? And if they're different, if there's an interaction, it means that how anxiety scores change over time differs across whether you receive treatment or not. And if it is significant and the change is lowering through the treatment, we can say treatment is effective. So this would be a mixed design, right? Okay, so there's other ways. This would be the best way to analyze this question. But there's also other ways to do it. And one would be, let's forget about pre-treatment. Let's just simply look at post-treatment and compare these two groups. And then see whose anxiety scores are lower after the treatment. Because we randomly assign, so what it's supposed to do is to make two groups equal because they're random, even though we know it's not always the case, but that's the main purpose of it. So if we simply just look at their anxiety scores post-treatment, what kind of analysis will we use? One way, because this is a between group analysis, and it's just one variable. We're not looking at over time. So one way ANOVA can address this question, but it doesn't consider the pre-treatment scores. And also, there's another way to look at it, and this is when I wasn't good at ANOVA. I hadn't taught this course. I only knew one way ANOVA, and I didn't know how to run repeated measure. I didn't know how to run mixed designs. So with my, I think, problem-solving method is that I'm interested in the change scores. What if I do post-treatment minus pre-treatment? Okay, so I have a change score. How much your score changes across these two timelines? And then I just simply do a one-way ANOVA, comparing the change scores. Not the raw scores, but the difference between the two time points. Does that make sense? Okay, so for example, 50 for the treatment group, and it's 49 for the control group. And then this group gets treatment, and then their score is 32 here, and then it's 48 here. So this is control. So what I did was like, okay, eyeballing, it looks like these two are different, right? It seems like the first one you decrease 18 points, the second one you only increase 1, so it seems like treatment worked. But to sort of want to have a significant test, what I did was I just calculated the change scores. So this was 18, and this was 1. And then I just ran a one-way ANOVA with the change scores. So I would calculate the change scores for every participant. So that's another way of doing it, is calculating the change scores and do a one-way ANOVA. So these are the 3 ways of doing it. One-way ANOVA with only post-test. This is one way. Split plot, or in other words, mixed design. So the one that Lauren mentioned. And then one-way ANOVA on different scores. So looking at how much scores they changed, they lowered, and then just using a one-way ANOVA to compare. And then the last one that I'm going to talk about today is Ancova. So what we can do is run an Ancova, compare these two, but controlling for the effects of their pre-scores. Okay, so I'll talk about what this is, what controlling covariate means. So this is what Ancova means. Okay, it's all analysis of covariance. And what we do is we adjust the outcome scores, the DB scores, based on the differences that are associated with covariance. So we want to hold all else constant. We want them to be constant at the covariate, using the covariate to adjust. So for example, okay, we want to compare 3 types of training groups. Let's say they're being trained to use SPSS. Okay, one group is a control group. We don't provide any training. We just say, go look up information. You'll be tested afterwards. You have a pre and post. And then one group is video demo group. So they go look up videos, or you assign them video modules, and then they learn the training from there. And then the third group is hands-on group. Like you have a TA instructor that teaches you how to run SPSS and do it together. So we want to see which group is most effective in terms of their SPSS skills. So, so what we can do is, okay, after they do the control, video demo, and hands-on group, we test them on their SPSS knowledge, and then they get a score. And then we can compare them on their skill levels after the training. So is there an issue with this kind of design? Christina?
Well, my question was going to be, like, what if they already had SPSS training?
Yes, exactly.
Oh.
So that's exactly the issue. We don't know if they have pre-existing skill differences. So there might be some people that already had training before that were already good at SPSS. So then we couldn't tell if it was the effect of the video demo group or the hands-on training method, or was it because of their pre-existing SPSS skills. So what we want to do is we want to control for that. We want to put everyone at the same level and then compare. Okay, does that make sense? Yeah, so we want to take out all the effects of their pre-existing SPSS skills. And so what we do there is there's 2 steps involved. Is we first figure out, okay, if what the pre-existing SPSS skill, how that's related to their SPSS skills after the treatment. So we would use a regression to figure out the regression line. So how those 2 are related. And then based on the regression line, we will slide them up or down the regression line so they start off with the same level of pre-existing skill. Their adjusted score is based on if your pre-existing skill is this. Does that make sense? Okay, so let's say the pre-existing skills for these 2 groups, these 3 groups, are like this. The control group, and then there's the video demo group, and then there's the hands-on group. So their pre-existing SPSS skills, like this one had 8 points, this one had 3 points, this one had 6 points. Let's say that. That's their pre-score. And this is their post-score. Let's say this was 15, this is 14, this is 9. Oh, this doesn't make sense. Okay. This is 20. Okay, so let's say this is their pre and post scores. And so we know that the control group started off with higher pre-existing SPSS skills, so that's not fair. And so what we want to do is to adjust their post scores. They're going to have adjusted scores. It's based off of on if they had the same pre-scores. So first we examine the relationship between pre and post. So we do a regression, and then based on the regression, we adjust their scores. So based on that, if they were to start off with the same pre-score, let's say 5, if they were all going to start off with 5, would we adjust this higher or lower? With the adjusted scores will be lower.
Yeah.
And then for this one, would it be higher or lower? Higher, because this was 3, and if we adjust them to have a 5, this would be higher. And then this, to adjust to 5, would be a little bit lower, so the 20 would be a little bit lower. Does that make sense? Okay, so I was trying to come up with an analogy, and this is what I came up with, but I don't know if it works with this group. Anyone play bowling? Yeah. Okay. Is there handicap in
Yeah.
bowling? So for those that are better, you sort of give points, right? So this is kind of like that. So you sort of readjust based on your past scores, so that you make the competition more close. Or like the betting, like when we bet for sports, it's like, okay, if this New England Patriots is playing against Cleveland Browns, I don't know if you follow sport. Of course, the Patriots are much better than the Browns, so we sort of like the Patriots have to win by 8 points for you to win. So you sort of adjust. So it's a similar concept to this covariance. So you adjust the scores based off of the pre-existing variable, and then you have new adjusted scores that would take out the effect of that pre-existing variable, and it would make all things constant, as if they started off with the same pre-existing score. So I'm going to show you a few plots, or how it works, like with a regression graph. Don't feel like you need to know how to calculate this, but just want to illustrate what we're doing here. So this is the DV, so this is the outcome variable that we're interested in, so like the anxiety, post-treatment anxiety scores. So, and this is the covariate. This could be related to their pre-anxiety scores. And so this, the red ones are the treatment means, are the means that we get after they've done the treatment. And so this is for one group, this is another, this is for another. But as we see, these 3 groups started off with different covariates, different levels of anxiety. So what we want to do is we want to control for the pre-anxiety scores. So we want to partial out the effect of that. And so what we do is we want to make them all equal on this covariate. So what we do is we first calculate the relationship between the covariate and the DV, and we get this slope. And then we use the slope to slope them down to like an equal covariate place. And then compare their dependent variable with the adjusted scores. So basically it's adjusting their scores so that they are compared as if they were equal on this covariate. So these are also some other examples in terms of how you might adjust the scores. So in terms of these 3, they're all on the same line, meaning that there's actually no difference between these 3. But if, in terms of on this covariate, they started off with different anxiety scores, so this would end up with a higher outcome post-anxiety scores than the blue group, than the red group. But if we were to adjust these three groups to start off as if they had the same pre-existing anxiety scores, and they would slide down to here, slide up to here, all lined up in this orange line, and then their DVs would be no different. Does that make sense? So this is another different scenario. So this is unrelated, but a different scenario in which if we measured their DV, so post-anxiety scores, they look all the same. However, they started with different pre-existing anxiety scores. And so this green group started with higher pre-existing anxiety scores than the blue group, than the red group. Okay, so if this is a scenario, there's three groups, we ended up with the same anxiety scores. Okay, if we just look at that scores, there's no difference. But if we say, hey, let's look at their pre-existing anxiety scores, take that into account. So there was one that had higher, and then one middle, and then one had lower anxiety scores. So which group would the treatment be most effective?
The one that had the greatest relative increase.
Yes, the one that had the highest anxiety scores to start off with.
Yeah.
So it would be like this green group. So if we slide them down based on the relationship between the covariance and the dependent variable, we would get the new adjusted variable here for the green, the blue here, and the red here. And if we use the adjusted variables, we could see that the red one is higher than the blue one, is higher than the green one. Does that make sense? So in other words, we're going to find another variable that we think is related to the outcome variable, and we're going to control for that. Statistically, make everyone equal on that variable, and then compare their adjusted scores so that it's fair game. Okay. So it seems like I understand a little, but not fully. Okay, so so when we report, it would be important to report the adjusted means, or you can report both, but just make sure you indicate it, whether they're adjusted means or the original means. These are the assumptions for one-way and factorial ANOVA. And if we're running an Ancova, we have 4 additional assumptions that we need to examine. And so one is the reliability of the CVs, so that's looking at the Cronbach alphas. So we want to have a consistent, reliable measure. And then the second one is linearity. Is this
Linearity. Yep,
linearity.
Yep.
Linearity. So linearity, we want the covariate and the dependent variable to have a linear relationship. And then the third one is lack of multicollinearity. I think you've learned about this in regression. And then last one is homogeneity of regression. So I'll talk more about these 4, what they mean. So the reliability of the CV, that's pretty clear. You just look at the alpha values. And here, they suggest that the alpha coefficient is 0.80 or higher, but I think other guidelines say that 0.70 is good enough. So that's Newley, which is I think the most commonly cited. I think it's Newley in 1970 that says, or 78, that says 0.70 or higher is good. So I would say 0.80 is ideal, 0.70 is good enough. And the next one is linearity. And so what we do for linearity is we examine the scatter plots, and we want to see if there's a curvilinear relationship. I don't know if you are familiar with what a curvilinear relationship is, so I'll draw what it looks like. So like a linear relationship is like this, like a straight line. And then a curvilinear relationship is when it involves like the x squared and stuff. So it's like, could look like this, could look like this. So these are curvilinear relationships. And so last time, I think I showed you some slides, graphs that briefly talked about like how to adjust for scores. You slide it down the slope, up the slope, so they're equal on the CV, on the covariate. And so if it's curvilinear, then it's kind of hard, it's weird, like in terms of sliding and stuff. So we want a linear relationship. So this is what we check. And so what we do is we get the scatter plots of the dependent variable and the covariate and take a look at it. I think this looks pretty linear. Others, a little bit, but nothing that looks like curvilinear. So we're like roughly okay here. So this is an example, but of course with these scatter plots, it involves so much subjectivity. So it's kind of like looking at normality, what is normal or not. So, but just wanted to give you an idea of what they mean when they talk about linearity. Multicollinearity. So that's when two or more CVs are highly correlated. So I think in regression, if the predictors are highly correlated, it can do evil things, and it can mess things up. What we should do is that if there are correlations that are very high between two covariates, to drop one, so that we only leave one left. So if there's many, like 3 of them and 2 are high, they're high, let them drop 2 and just leave 1. So because it adds very little adjustment, removes the degrees of freedom of error, and it causes potential computation difficulties or strange outcomes. So how do we test for it? One way is to use a factor analysis function in SPSS and make sure the squared multiple correlation is less than 0.50. And so this is done through factor initial communalities. So I will just, we won't do it, but just in case in the future you want to deal with this evil thing or examine, this is where to do it. Go to Analyze, Dimension Reduction, and Factor. So this is usually where we do factor analysis. And just put in the variables that you're interested in examining. So if it's a regression, put in the predictors. If it's covariates, put in the set of covariates. And choose extraction, and under extraction, select principal axis factoring. And then after you hit continue run, you will have this table that's communalities. And you look at the initial column, and if it's over 0.50, it's
Multicollinear.
yes.
Yeah.
And then so then we would eliminate some of the.
So all 3 of those were multicollinear to each other.
Yes, so this we would then drop 2 and keep the one that's most highly correlated with DV. Homogeneity of regression. So what this says is that we want the same slope between the CV and the DV for all levels of IB. This sounds a little bit complicated. There's CV, IB, and levels of CV, DV, and levels of IB. So in essence, this is what it looks like. So we have the different slopes last time in the graphs, where we used to adjust the values so that they line up on their CV. So this is a case of homogeneity of regression, means that they parallel each other. They have the same slope. So we would be able to adjust. But if it's not, if it's something that looks like that, it would be really hard to adjust. Because look, if we're adjusting here, this is increasing, this decreasing, and this decreasing at a different slope. If we're adjusting here, this is decreasing, these are increasing. So then adjusting it to this versus this would have very different implications. So this is clearly a violation, an assumption that we need to adhere to. So this is something that we would examine, and we won't go through how to examine it. There's different ways of examining it, but if you are interested, they're on the slides, and I think there's some examples on the pages of the slides that I hide. So if in the future you're ever interested, that's a resource to go through. But just mostly wanting you to know the concept and why they apply. One last thing that I think is important is how do we choose covariates? What are some things that we consider when we're choosing covariates? And one is that the CV must be independent of treatment. So it's something that we should consider before we do the study. So if we're looking at a study that involves therapists, okay, we might think about factors beyond our outcome variable that we're in our IV that factors beyond our IV that might influence or be related to our outcome variable DV. So it could be the therapist's age, or it could be the number of years that therapist has conducted therapy, or the number of practicum hours. Looking at what kind of factors that may relate, and then collecting data on that, so later on we can use it as a covariate to tease out the influence of that variable. And we don't want a large number of CVs, because sometimes you might think, well, CV, like covariates, they're so cool. Like, okay, you just drop it in that box, and then it will take out the effect of that. And I wanted to take out the effect of gender, ethnicity, age, this and that, so I'll just put all my variables in there. And then it will control it really well, and so what is left is the influence of the independent variable. But if we do that, you might gain some power in smaller sum squares, but it is offset by the loss of degrees of freedom. The more covariates you add in, the less degrees of freedom you have, and then the harder it is to detect a significant p-value. So usually we add a few CVs, but not too many. And so in terms of deciding which ones to add, this is what we look at. We look at the correlations. So we want the covariates to correlate with the dependent variable, and we don't want the covariates to correlate with each other. So, make sense? Okay, so next I'm going to give you a pop quiz. No, okay, not yet. Okay, so the next one. Okay, so strategies. So in terms of choosing some additional things, theoretical grounds, knowing the literature, and so you kind of know what kind of sources that should be controlled for. And then there's also statistical considerations, so you look at the correlations among the CVs and select only one among those that highly correlate with each other, and choose the one that most highly correlates with the dependent variable. So this is your pop quiz. And so here is a study, and here's the DV, here's the IV, here's some potential CVs that we can use, covariates, and which one would you use, and how would you make that decision? So the research question is, we want to compare the effectiveness in treating anxiety, I spelled it wrong, across different treatment modalities. And so the outcome variable is the post-treatment anxiety levels. So we want to see which one's higher, which one's lower. And then the independent variable is the different types of treatment, like CBT, person-centered, psychodynamic, etc. So here are some potential CVs, and here I give you the correlations of how it correlates with the DV, post-treatment anxiety score. So the first one is the client's pre-treatment anxiety level. So the pre-treatment anxiety is correlated with the post-treatment anxiety at a 0.53 correlation. And then the second one is the number of years the therapist has been doing therapy, and it's correlated with a post-treatment anxiety level at 0.03. And the third one is the number of sessions that they received during the treatment process, and this is correlated at 0.35. So which covariant or covariates would you choose?
Pre-treatment anxiety level
Pre-treatment.
and
Okay.
session?
Okay, so there's pre-treatment anxiety level, and then there's session. Okay, so anyone would choose therapist experience.
That
Why not?
correlation level.
The correlation is very low. So it doesn't seem to relate much with their outcome. So why do we need to put that in if it's not related? It's not going to take out much. It's going to take away degrees of freedom. Okay, so this leaves us to 2. So we think that 0.53 and 0.35 is reasonably high. So it could impact the outcome variables, and want to control for those. And then what would be what would be a factor that you don't have information about, you would want to find out before you decide which one or whether the two to use as covariate?
If they're correlated.
Yeah. So we would see if these two are correlated. If we can use a correlation, or we can use that communality test to see if they're highly correlated. If they are, then we might run into the issue of multicollinearity, and so we would want to just use one. So you all passed the test.